Hello, everyone. Thank you for being with us here in the Research Papers room, for joining us at the Research Papers competition sponsored by Major League Baseball. Hope everyone's enjoying their box lunches. I'm pleased to introduce our next speaker in the last presentation of our morning session. We have Michael Alcorn presenting on batter-pitcher 2VEC, statistic-free talent modeling with neural player embeddings.
Hi, everyone. Thanks a lot for being here. I'm absolutely thrilled to be speaking with you today. If you had taken a look at my life a little over 5 years ago when I was a recent dropout of a PhD program in evolutionary biology, I don't think you necessarily would have predicted that I would be presenting at Sloan ever. But if you look back a little bit further in time, so this is a picture of me on my 9th birthday where I'm receiving the PC game NFL Math as a birthday present. Almost feels like destiny that I'd be here. So yeah, today I'm going to be talking to you guys about a project I worked on called batter-pitcher 2VEC. But before I get started, I want to point out that my slides are available on my website. I like to include lots of links to additional resources. And so if you want to follow along on your personal device, you can do that. Additionally, I have a Jupyter notebook up on GitHub that will allow you to reproduce all of the results I'm going to be talking about today. If you have a standard deep learning setup already installed on your laptop, you could probably start the notebook now and have it finished by the time I finish my talk. So the idea of quantifying player talent is not a new one, particularly in baseball. Everyone in here is probably familiar with wins above replacement, which attempts to assign a value to a player that reflects how much they're contributing to their team's overall record. And there's also the proprietary Pacoda algorithm, which uses neighborhoods of players and an age correction to try and forecast how well a player is going to do in the future. And there's also the proprietary deserved run average, which is sort of a corrected ERA, in that it uses a linear model that tries to account for different contextual variables to assign the appropriate amount of blame to pitchers. And so quantifying player talent, or what's also referred to as style, has come up in other sports as well. And so these are all Sloan papers that have addressed this topic. And I separated them into two columns that sort of reflect two overarching themes I've seen to address quantifying player talent. On the left-hand side, we have what I call aggregate and extract. And so what they're essentially doing is aggregating a bunch of data, so like sort of counting different types of outcomes, and then applying some typically unsupervised learning algorithm to that aggregated data to extract features that somehow are describing the data and sort of represent style. While these latent feature approaches are really powerful, the disadvantage of aggregating is that you lose any sense of context. And as we all know, as sports fans, context is really important when you're trying to understand how an athlete behaves. On the right-hand side, we have models that do consider context. And the way they do that is they're trying to model different sort of events during a basketball game by considering how different players are interacting on the court. But these models are strictly linear, and so they're not taking advantage of these latent variable approaches. But we know, right, that players have there's these hidden variables that describe player talent. So by ignoring those variables, they're sort of making the problem harder than it has to be. And what I'm going to argue today is that this neural embedding framework allows you to marry the best of both worlds from these two approaches. You have the powerful latent features to model talent, and then you're also considering context of different players and predicting outcomes. And so why are neural networks particularly appropriate for this task? It's because they're really good at what's known as, or what's referred to as, representation learning. And representation learning is sort of another way of saying automatic feature extraction. And to make that a little more concrete, I want to talk about the 2012 ImageNet competition. In this competition, a bunch of computer vision researchers got together and tried to basically build models that would predict or classify images as accurately as possible. So whether or not there was a dog in the image, a cat, a car, etc. The winner of this 2012 competition was a convolutional neural network, and it was the first year that this type of model won, and it sort of blew everything out of the water. And while that's sort of cool in itself, what's really interesting is if you look at the internal workings of the model, what you can see is, so if you look at these filters on the right-hand side, this is what the model was learning. You can see that it was learning to detect things like edges, and they're oriented in different directions, color gradients, and other types of patterns. And so I want to emphasize that the point of this model was not to extract features. The point of the model was to predict. It was to optimize some prediction problem. But as a byproduct, it learned to extract features that were important and interesting. So one area where these representation learning concepts have been particularly useful is in the field of natural language processing. And so when you have categorical data in machine learning, like words, the way you typically represent those categorical data is by using what's called one-hot encodings. And the way you do that is, so if we have, for example, 3 words in our vocabulary, dog, cat, and constitutional, for each of those words, you would assign them a vector that's all zeros except for a 1 that is a 1 where the index for that particular word is. The problem with one-hot encodings is that they're implicitly saying everything in the set is equally similar or dissimilar, which we know is not true, right? So dog and cat are clearly semantically more similar than either of them are to constitutional. And so the way neural network models are typically designed for natural language processing to address this fact is they use what's called an embedding. And so what you see right here is a recurrent neural network. That's a standard recurrent neural network architecture for doing natural language processing, where you supply words 1 token at a time, and those are the one-hot vectors, and then they are embedded into a dense vector. And what I mean by that is they are put into a vector that's typically much smaller in dimension than our vocabulary, and it has a bunch of numbers filled in, so it's not all zeros. It's like dense, right? And so one thing to note, though, is that these natural language processing models are sort of trying to do 3 things at once, right? They're trying to learn the meaning of words, they're trying to learn how words come together for like syntax, and they're trying to learn how the language is relevant to the task at hand. And so this model known as Word2Vec tries to outsource that learning word meaning task. And the way it works is you provide it a corpus of text data, so let's say like all of Wikipedia, and I'm going to be talking about just the architecture on the left here. And you pass over it a window, in this case a size 3, and for every 3 words, you take the word on the left and the right, you embed them into a vector, you add those vectors together, and then you try and predict the word in the middle. And when you do that, you get words that have really intuitive, word vectors that have really intuitive properties, where words that are similar in meaning are close to each other in this space. But what's also really interesting is that they have analogy properties. And so you can calculate the analogy x is to y as blank is to z by doing vector algebra, as I show there. And all these analogies on this page were obtained from Red Hat data. And so you can see, for example, that if you take the word vector for Firefox, subtract the word vector for Linux, add the word vector for Windows, you get a word vector that's very close to Internet Explorer. So this embedding concept is very powerful. And so what I wanted to know is, can we apply these representation learning concepts to baseball players? And so the way I did that is I acquired some at-bat data from retrosheet.org. You can see the numbers there. And so each data point, essentially, in my data set consists of a batter, a pitcher, and the outcome. And what you see here is all of the different possible outcomes. And so it's just, like whether or not it was a hit, who's the first defender to field the ball, strikeout, walk, etc. And this is the actual model, and so hopefully you'll see the resemblance to Word2Vec. But what I essentially did is you take your one-hot encoding of your batter, your one-hot encoding of your pitcher, you embed them into separate batter and pitcher embeddings. I pass those through a sigmoid function, concatenate those vectors together, and then try and predict the outcome of the at-bat. And so that's the math right there. And then I optimize the average cross entropy, which is the same as maximizing the likelihood of the model. So one interesting thing to note is, people hear neural networks and they think, like complex or whatever. But if you actually compare the number of parameters in batter-pitcher-to-vec to a multinomial logistic regression model doing the exact same task, it actually has a fifth of the parameters. And so that's kind of interesting. I want you to keep that in mind as I go forward. And so the first thing we can do after we've trained the model is try to visualize these embeddings and see if they're doing anything that resembles reality. And so what you see here are the first two principal components of the discovered batter embeddings. And what we can see is, like players with high singles rates are on the opposite end of players with low singles rates, likewise for home runs. And we see that batters are clearly being separated in their handedness. So the model's like clearly learning something about reality, but this is like not super interesting in itself, right? Because we already keep these stats, so like that's not really telling us much. What's a little more interesting is you can take a look at the neighborhoods of these embeddings and see what happens. And so what you see here is a two-dimensional T-SNE map of the batters on the left and the pitchers on the right. And I don't know if you can necessarily read that. What we can see is like D. Gordon and Ichiro Suzuki are really close to each other in their neighborhood. Mike Trout and Paul Goldschmidt are really close to each other. And I think maybe even more interesting, because it's kind of a harder problem, I feel like, because the stats aren't necessarily there, is Dellin Betances and Aroldis Chapman are in a neighborhood. And so if you follow baseball, you know that these guys are like really powerful relief pitchers. And so the fact that the model sort of captured that just by trying to predict the outcome of different batter-pitcher matchups is really interesting. One sort of fun thing we can do is we can do actually player analogies. And so what I did here is I took the vector for Mike Trout, who is a right-handed batter, subtracted the average vector for all right-handed batters, added the average vector for all left-handed batters, and got a vector that's very close to the vector for Bryce Harper. And so you can think that Bryce Harper might be considered Mike Trout's left-handed doppelganger. And that's just another piece of evidence that these embeddings are learning something real and interesting about these players. So, but the ultimate test of whether or not these models are capturing something interesting is whether or not they can predict something that they haven't seen before. And so to test that, I wanted to compare it to some sort of baseline. And the baseline I came up with was what you see here. I basically built a co-occurrence matrix for batters and pitchers, which is a row is a batter, the columns are the outcomes, and just counted those up. And then I also had a little bit of a smoothing factor where I basically added one at-bat to the player and distributed the probability mass of that at-bat across like all of the outcomes. That's an average over all batters. And so the naive prediction probability then was me just averaging the probability from the batter co-occurrence matrix and the probability from the pitcher co-occurrence matrix. And what we see is that batter-pitcher DVEC significantly outperforms the naive model, and that's at the less than 0.001 level. And so that's cool and all, but what I think is actually also really interesting is that the multinomial logistic regression model, which had 5 times the number of parameters, actually performs slightly worse than the naive approach. So this batter-pitcher DVEC is like doing a really good job, it seems like, of accurately modeling talent. And so yeah, the test set here was previously unseen matchups, so batter-pitcher matchups that were not in the training data and from a season that I hadn't looked at all. So it's like completely new data, essentially, to the model. And so I think this batter-pitcher DVEC demonstrates that this neural embedding framework is a really powerful framework for modeling player talent. And in fact, I actually think it could be applied to all of these papers that I talked about at the beginning of my talk. But I'm going to leave as a homework assignment for the audience to think about how exactly you would implement that. But if you want to talk about it, you can feel free to reach out to me. So I actually first developed batter-pitcher DVEC in the spring of 2016 and didn't, this conference wasn't on my radar, so I didn't think to submit a paper until after the 2017 deadline. But in the fall of 2016, I wrote a blog post applying reinforcement learning to NFL play-by-play data, and in it, I proposed you could use team embeddings to model the outcome of yard distributions on plays, and then use that in an adversarial framework to, strategically pick plays. And then, really interestingly, independently, there's this paper at 2017 Sloan on data-driven ghosting using deep imitation learning, where they were trying to model how soccer defenses would respond to the offensive movement. And in it, they used team vectors to account for different team style. And so that's really cool and interesting. But one thing I want to note is that these team vectors are inherently fragile. And what I mean by that is that they're trying to model team dynamics that can really are subject to change in real sports. And for example, if a coaching change happens, if there's a trade, if there's an injury, if a certain player starts getting more or less minutes just because of how they're performing, all of those dynamics will cause these team vectors to break. And so what I want to propose is that these player embeddings can allow you to get around that obstacle. And so in this 2016 paper on classifying, another Sloan paper on classifying NBA plays using neural networks, what they did was they took spatiotemporal data of NBA spatiotemporal data and turned it into images where they had the players mapped to XY coordinates, and then they colored the players by sort of doing a secondary task and assigning them to a position. And by assigning them to a position, they're losing any sense of identity about these players. And this is a common problem that you see cropping up in papers trying to model spatiotemporal data in sports. They're always concerned about how you appropriately assign the player order so you can capture the dynamics accurately. And I think that this neural embedding framework could allow people to model spatiotemporal data while simultaneously accounting for individual player talent. And the way you could do that is to, again, imagine that we have a bunch of XY coordinates about where the players are, and we could then turn that into a sequence of images, quote-unquote images, where the XY coordinate would correspond to the player's location in space, and then you can use the channels, the Z dimension, as the embedding. And by doing that, you can have your sequence of images, right? You could pass that into a recurrent convolutional neural network and try to predict whether or not the team made a basket, the offense made a basket. And theoretically, if you got a model like this working well, it could essentially serve as a model for doing model-based reinforcement learning, which I think is a really exciting prospect, because at that point, you can essentially have an artificial intelligence designing plays for you. And I think if you follow the AlphaGo thing, you know that these algorithms that are learning to play at superhuman levels end up employing these really creative and unhuman strategies, right? So I think it would be really fun and interesting to see how AI might design an offensive play. But on that little bit of sci-fi, I'm going to end, and I'm happy to take any questions.
So now for the Q&A, we will walk around with mics, so just raise your hand, and we'll come to you.
Hi, thanks. I was just curious, did you incorporate game state into your model, especially in the predictive part?
I did not, but that's easily something that you could include. I was trying to make something that was sort of as basic as possible for a proof of concept. But yeah, you could totally incorporate. If you saw my the slide, does this go backwards? In this slide that I proposed doing using team embeddings for modeling NFL plays, I had things like down and distance and the number of players rushed as additional contextual variables. So you could totally include those, and that might give you more accurate prediction capabilities.
Hi, at the back. Hi, I really enjoyed your talk. I was just wondering, how consistent are players in their performance? And did you try cross-validate to see whether you could rediscover whether one player would be similar to themselves in a different data set?
So do you mean how consistent are the embeddings?
Yes.
Yeah, so the space is going to be different each time you train it. And so that would be, in the paper I talk about sort of how, I talk about how if you trained a data set on minor league baseball players, how you would maybe be able to map that to a major league baseball player. And the way you would hypothetically do something like that is, so if we have these trained embeddings for the major league baseball players, you'd train a separate set on minor league baseball players, and then you train a third model that maps the minor league baseball players who made it to the major leagues, and that would allow you to go from one state to the other. So you could do something like that from season to season if you wanted, but that's that would be a challenge that you have to address.
Thank you.
So this stuff looked really cool. So I think one of your selling points here is that you can actually do some sort of analogic reasoning with with your vectors. So those analogies are sort of fundamentally extrapolation, right? You're taking a particular player and then you're sort of changing something about them, turning it into something else. Did you take a look at, say, some kind of extrapolation where you could actually have some validation? So for example, turning a relief pitcher into a starting pitcher, turning a starting pitcher into a relief pitcher, and then actually comparing that to the real outcome?
I did not, but I've thought about that, and this data is all available. I encourage people to play around with it. I would love to see any sort of analogies that people can come up with. I think that's like a really interesting idea.
Just like a short follow-up there. Do you have a sense of what analogies you think would be sort of fragile, and what sort of analogies you think would you could actually trust coming out of this particular embedding?
No, I don't think so. I think anything's potentially game because it's essentially trying to model player talent. So you're trying to, what you're asking, I guess, is like what things that we consider talent, what variables that we consider talent aren't actually talent. And like I don't actually know the answer to that question, right? It'd be interesting to experiment and see what the actual answer was.
Okay, we can take one more question.
Hi, I was wondering how fragile or robust the learned embeddings were to different initializations.
Yeah, so those are, the actual embedding space is gonna change because the way these models work is you randomly initialize a weight matrix, and what's happening is the one-hot encoding is like essentially giving you a row or a column out of this matrix. And then it's trained by stochastic gradient descent, and so it's being optimized, and these models have like all these different minima, local minima. And so yeah, your embedding space is gonna change from training to training, so you really have to consider the model in a particular context, basically, the embeddings. You have to compare them all from one same like training round, I guess.
So how much did it train, or did it change from training round?
So I trained it once, and you initialize it to like these random vectors, and then I trained the model for 100 epochs, and so they gradually got optimized through all of that training by trying to maximize the likelihood of the model.
Okay, thank you so much. Everybody join me in thanking Michael Alcorn.
Thank you.